Welcome to Chapter 2 of our course. Today, we are going to explore the fundamental world of digital filters, focusing on how we process discrete signals through mathematical frameworks. Let's begin with the foundation: discrete linear time invariant systems, or LTI systems. In simple terms, a linear system uses a mathematical operator to transform an input signal into an output signal. We call a system discrete when it operates on a sequence of individual data points, denoted as xn, to produce a discrete output yn. For a system to be considered linear, it must follow two rules: scaling and superposition. If we scale the input by a factor alpha, the output scales by the same amount. Similarly, if we combine two different inputs, the output will simply be the sum of their individual responses. This predictability is what makes linear systems so powerful in engineering. The second half of LTI is time invariance. This property means that the system's characteristics don't change over time. If we delay our input by a certain amount m, the output remains exactly the same, just delayed by that same amount. Essentially, it doesn't matter when you start the experiment. The system reacts consistently regardless of the time origin. When a system is both linear and time invariant, we can fully describe it using a single sequence called the impulse response, denoted as Hn. Think of Hn as the system's unique fingerprint or its DNA. Once we know it, we can predict how the system will react to any possible input. This prediction is done through a mathematical process called convolution. Convolution is the most fundamental operation in signal processing. It tells us that the current output value is a weighted sum of the past values of the input signal. Mathematically, we express this as yn equals the sum of hk multiplied by x and k. So, what exactly is the impulse response Hn? It is the output we get when we feed the system a Dirac pulse, which is a single spike at time 0. You can visualize the convolution calculation as taking the impulse response, flipping it in time, and sliding it across the input signal, calculating the overlap at every step. Let's look at a concrete example. If we take a rectangular pulse as our input xn and a decaying exponential as our impulse response hn, the resulting convolution n can be solved piecewise. As you can see, the output remains 0 for negative time, grows during the overlap, and then decays once the input pulse has passed. A couple of important remarks here. First, correlation and convolution are mathematically related. You can think of correlation as convolution with a time reverse signal. Second, sinusoids are eigenfunctions of LTI systems. This means if you put a sine wave in, you get a sine wave with the same frequency out, though its amplitude and phase might be adjusted. Now, we move to a crucial tool, the Z-transform. Much like the Laplace transform is used for continuous systems, the Z-transform simplifies the analysis of digital filters. It converts discrete time signals into a complex variable Z-domain. We define it as a power series where xn is weighted by z to the power of negative n. A Z-transform only exists if the infinite series converges. The region in the complex plane where this happens is called the region of convergence, or ROC. Typically, this region takes the shape of a ring or an annulus centered at the origin, bounded by two radii, R1 and R2. To determine where the transform converges, we use the Cauchy criterion. This mathematical rule states that a series converges if the limit of the nth root of its terms is less than 1. We can apply this to our Z-transform summation to find its boundaries. By splitting the Z-transform into two parts, one for negative time and one for positive time, we can analyze convergence separately. For the positive time series, x2, z, applying the Cauchy criterion shows that it converges whenever the magnitude of z is greater than a certain radius R1. Similarly, for the negative time part x1, z, we perform a change of variables. The math reveals that this part of the series converges when the magnitude of z is less than a second radius, R2. This creates our upper bound for the convergence ring. In summary, R2 is determined by the behavior of the signal as time goes to negative infinity, combining both parts. We confirm that the z-transform generally converges within a ring where the magnitude of z stays between R1 and R2. How does this relate to the Fourier transform we already know? If we look at the discrete time Fourier transform, d to ft, we see it is a summation involving complex exponentials. This looks remarkably similar to the z-transform formula we just discussed. In fact, if we evaluate the z-transform specifically on the unit circle, where the magnitude of z is exactly 1, it is identical to the Fourier transform. This means the frequency response of a digital system is simply the z-transform evaluated as z moves around the unit circle. Let's look at an example using a causal exponential signal. By applying the definition, we can sum the geometric series to find that the z-transform is z divided by z minus a. Note that this specific transform is only valid outside the circle defined by the pole at a. Visualizing this in the complex plane, we see a 0 at the origin and a pole at the value. The unit circle is shown here in blue. As we move around the circle, the distance from any point to the pole and 0 determines the frequency response at that specific frequency. Quantitatively, the magnitude of the frequency response at a frequency f0 is the ratio of the distances from the unit circle to the 0, R1, and the pole, R2. The phase, or argument, is simply the difference between the angles formed by these vectors. This principle generalizes to more complex systems. If a system has multiple poles and zeros, the total magnitude is the product of the distances to the zeros divided by the product of the distances to the poles. The phase is calculated by summing the angles of the zero vectors and subtracting the angles of the pole vectors. The z-transform has several useful properties that simplify our work. For instance, a delay in time corresponds to multiplying by z to a negative power. Most importantly, convolution in the time domain becomes simple multiplication in the z domain, which is why we use it so often. Here is a reference table for some common causal functions. You can see the transforms for a simple impulse, a step function, a ramp, an exponential, and a sine wave. These standard pairs are the building blocks for analyzing more complex digital systems. Sometimes we need to go backward from the z domain to the time domain. One way is the power series development method. By expanding the transform as a Taylor series in terms of z inverse, the coefficients of each term directly give us the samples of our signal xn. In this example, we take a transform involving an exponential function. By using the known Taylor expansion for e to the power of y, we can rewrite the expression as a summation. From there, we can easily identify the sequence for xn based on the coefficients. Another approach is the division development method. If the z-transform is a ratio of two polynomials, we can simply perform long division. By dividing the numerator by the denominator in terms of z inverse, we produce a sequence of terms one by one. The resulting quotient from that long division gives us the values of our signal at each time step. For example, the coefficient of z to the negative 1 is the value at n equals 1. The coefficient of z to the negative 2 is the value at n equals 2, and so on. A third and very common method is partial fraction expansion. If the degree of the numerator is less than the denominator, we can break a complex fraction into a sum of simpler fractions, each corresponding to one of the system's poles. We calculate residues for each pole to determine the weight of each fraction. Once decomposed, we can use our table of standard Z-transforms to easily find the time domain equivalent for each simple piece, even if the system has multiple or repeating poles. Moving from abstract math to implementation, we use difference equations. A difference equation relates the current output y in to past outputs and current/past inputs. This is the recipe a computer follows to process a signal in real time. By applying the Z-transform to the difference equation, we can derive the transfer function hz is defined as the ratio of the output transform to the input transform. As you can see, this results in a ratio of two polynomials made of the coefficients b and this diagram visualizes how the difference equation is structured. The signal flows through a series of delays, represented by z inverse, and is multiplied by coefficients before being summed together. This is the architectural blueprint of a digital filter. The transfer function hz can be factored into its poles and zeros. The b coefficients determine the zeros, and the coefficients determine the poles. The gain k is simply the ratio of the leading coefficients. This factored form tells us everything about the filter's stability and frequency response. Let's look at a practical example. For this specific difference equation, we derive a transfer function with a zero at -1 and a pole at +1. In software like MATLAB, we can define these using two arrays of coefficients, a and b, and visualize them using the spline function. Here is the resulting spline plot. The O represents the 0 at -1, and the X represents the pole at +1. These positions on the complex plane give us an immediate visual sense of how the filter will behave across different frequencies. Beyond pole zero plots, we often want to see the frequency response directly. Using MATLAB's Frex function, we can generate these plots showing the magnitude and phase. Notice how the magnitude changes as we move from low to high frequencies. A critical consideration is stability. A system is stable if a bounded input always produces a bounded output. For a causal digital filter, this translates to a very simple rule. All poles must lie strictly inside the unit circle on the Z-plane. If a pole moves outside, the output will grow infinitely. Now let's look at how we actually build these. Digital filters are generally categorized into two types, FIR and IR. A finite impulse response, FIR, filter, shown here in its direct structure, only uses the input signal and its delayed versions. Because it has no feedback, it is always stable. There are different ways to arrange the same math. This is the transposed structure of an FIR filter. While mathematically identical to the direct form, it might offer different performance characteristics in terms of hardware efficiency or numerical precision. In contrast, infinite impulse response, IR, filters use feedback, meaning the output depends on both previous inputs and previous outputs. This allows them to achieve much sharper filtering with fewer components, though we must be careful to ensure they remain stable. We wrap up with a typical second-order IR structure, often called a biquad. By choosing the right coefficients for A and B, we can create almost any standard filter type, like low pass, high pass, or band pass. This concludes our overview of digital filters and the Z-transform.